All right, ladies and gentlemen. So I realize that we have already looked at these two problems. I'm not sure that we actually had the full time to finish this one, but the reason I just want to pull this slide up to start with is just to make sure that you are aware that doing these problems is really not something that is all that different from the stoichiometry that we did in chapter 3. Okay? The only reason these problems are in chapter 4 as opposed to chapter 3, okay, is number one, because they're dealing with a precipitate, okay? And in number 2, for example, I did not tell you which compound I was talking about on the product side. You had to use your solubility rules to figure out what the precipitate was. So that's reason number 1. Reason number 2 is that the problems involve molarities, okay? And we had not talked about that yet. But once you get down to the actual math of it, the math is no different than what we did in chapter 3. Okay, and we're going to see more of that today. Okay, so the first thing that I want to do is look at this problem. Okay, I'm going to give you some foundation on it, but then, you know, you're gonna do it for the most part on your own. All right, so let's look at this. It says a 1.42 gram sample of a pure compound with the formula M2SO4. Let's stop there. Do we all know that there is no element M? Nod your heads. Okay. Think of M as standing for mystery element. Okay? All right, so this element, or this compound, is dissolved in water and treated with an excess of aqueous calcium chloride. Okay, so let's think about this for a second. This is reactant number 1, and that is my other reactant. Okay, when you have compound plus compound, what type of reaction are we dealing with?
Double replacement.
Double replacement, very good. Okay. Let's keep reading. Resulting in the precipitation of calcium sulfate. Okay, so not only are they giving us one of the products, they're telling us that that is the one that will be solid. That is my precipitate. Okay, now you'll notice they did not give us the other product, which means you're going to have to come up with it. And if you're at all concerned about, well, I don't know what M is, you don't need to know what M is. Tell me, what's the charge of M in this compound, whatever it is? +1. That's all you need to know to be able to predict products. Okay, so let's do that. You guys write out a balanced equation. Okay, so that's what your balanced equation should look like. All right, and again, they told us that this, the calcium sulfate, would be our precipitate. Okay, so let's go back and let's actually read the rest of the question here. Okay. All right, it says, the precipitate, this one, was collected, dried, and found to weigh 1.36 grams. Determine the molar mass of M and its identity. Okay, well, tell me this. When we pull a molar mass off the periodic table, guys, what are the units for that? Grams per mole. You're right. All right, I'm just going to write that down. Grams per means just divided by. And here's the thing. You may never have done this before. If you are supposed to find the molar mass of some kind of unknown, which means you can't look to the periodic table because you don't know what it is, you can get it if you have these two pieces of information about that unknown, okay? Or maybe an entire compound that contains that unknown. So what I mean is, if I know the mass of something containing my unknown and I know how many moles that is, I can simply divide those numbers and voila, there is my molar mass. Okay? So look at what the problem gave us. We have the number of grams, we have a mass. There must be some way to find moles. All right? So let me go back to our balanced equation here. All right, we are told that the precipitate, calcium sulfate, has that mass. All right? If I can find moles of this guy, I can solve this problem. Or I can at least find the molar mass of that compound. Okay? You're going to have to do some stoichiometry. Take what you're given and get to moles of M2SO4. Tell me again, guys, what were the units of molar mass again? Grams per mole. Grams divided by moles. Okay? We were given the mass of this guy. Is that my answer? Why not? Right. That is the molar mass of this whole compound. What do you suggest I do next? We need to get down to just M. Yeah, let's subtract the mass of SO4. So 1 sulfate, 4 oxygens, okay. Is that my answer? Why not? Right, because there's 2 M's, so what do? Divide it by 2. All right, so that's what I get for the molar mass of M. How are you going to figure out what element it is? Look on your periodic table. And what element is that?
Sodium.
Yeah. That molar mass is closest to the molar mass of sodium. And guys, think about what we said at the very beginning. When we didn't know what M was, we said, okay, well, we know at least that it has a +1 charge. Does this match that description? Yeah, it does. Okay. So there you go. Oh, sorry. Sorry, that should be 1.42. Sorry, my bad. That was the mass of the compound given to me in the problem. My apologies. Does it make sense now? Okay, sorry about that. Okay, now, the reason that I specifically wanted to go through this problem with you is because this is our next lab, okay? We're going to run a reaction with some kind of unknown. We're going to collect a precipitate. We're going to let it dry overnight, measure its mass the next day, and we're going to do this exact thing. Okay, so this is our next lab. So we have looked at precipitation reactions. We're going to look at our next type, which are acid-base reactions. Or let's use a better word, neutralization reactions. And before we even talk about the reactions, let's make sure that we know a few definitions. Acids will sometimes be defined as hydrogen ion donors, things that give away their hydrogen ion. Sometimes you will see it defined as a proton donor. And let me explain to you why we're using the word proton. Look at your periodic table and look at specifically hydrogen. How many protons does hydrogen have? Okay. How many neutrons does hydrogen have? 0. Okay. What does a +1 charge mean? What does that mean? What happened? It lost its 1 electron, so it has no neutrons, no electrons. Ladies and gentlemen, a hydrogen ion is nothing more than a proton. Okay? Did I blow your minds? It's okay. So that's why an acid is sometimes defined that way. And if acids are proton donors, that means bases, the opposite, must be proton acceptors. And at least for the time being, most of the bases we will deal with will contain OH. When we get a little later in the year and we get into some really heavy-duty acid-base stuff, we will start seeing a lot of bases that do not contain hydroxide, but we'll get there when we get there. All right, so this particular example, okay, of a neutralization reaction, acid plus base, okay, that's true for any neutralization. In this particular case, we get a salt and water. Some of your Chem 1 classes defined neutralization as acid plus base yields salt plus water. Well, guys, all acid-base reactions do not produce a salt and water, okay? So I want to make sure that you understand neutralization, focus on the reactants. That just means acid plus base. Stop there. Okay? Now, let me say something that I said to you last class. On our next test, you will be given problems in the free response where I give you reactants in words only, and your job is to get down to the net ionic equation. If you come across a situation where it's strong acid plus strong base, save yourself some time on your test. If it's strong plus strong, this is the net ionic equation every single time. All right? You'll notice I did not write out that middle step where we do the complete ionic equation. But if I did and crossed out my spectator ions, this is what I would end up with. Okay? Aqueous, again, dissolved in water, soluble, 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 not. Don't ever split up water. Okay? Water is just H2O. Leave it as is. Okay? So, good test-taking strategy on our next test. Strong plus strong, you can immediately go, okay, I know what that net ionic equation is, and move on to the next question. All right? Little bit of vocabulary. When we take a neutralization reaction into the lab, we call it a titration. And there's some vocabulary with this. First of all, do you all know the name of this piece of equipment? It's a long, skinny tube. It's open at the one end and has a valve on the other end. Do you know the name? It's called a burette. Okay? And it doesn't have like a French pronunciation, burette. No. Okay? It's just a burette. So what you would have is maybe your acid is up here and your base is down here, or it could be the reverse, base up here, acid down there, doesn't matter. But there's some vocabulary you need to know. Whichever substance is in the burette that is what we call our titrant. Okay, not tyrant, titrant. Whatever, could be the acid, could be the base, whatever is down here in the flask, that's our unknown, that is called your analyte. And the whole point of a titration is to get to a certain place, a certain point. It's called the equivalence point. Okay? And for those of you that have printed out the PowerPoints, I made a change yesterday to what is in this set of parentheses. I wanted to be a little bit more specific. The equivalence point is when you have equal moles of H plus and OH minus. Think back to that previous slide where we had the net ionic equation. When those two things are equal, you are at the equivalence point. So if I had 10 moles of H plus down here, as soon as I've added 10 moles of OH minus, I would be at the equivalence point. Now, why do we care? Because that's going to be important when we start doing some calculations, right? Because think about it, guys. If you're given in a problem enough information to find one of these pieces, if you're at the equivalence point, that means you know the other piece as well. Just a little bit of verbiage here. Sometimes a word problem will specifically say, we are at the equivalence point. But sometimes they're going to be a little bit more cryptic, and they'll say something like, this amount of acid is required to neutralize this base. That's code for them telling you we're at the equivalence point. Okay. So I just wanted you to be aware of that. Okay. Do any of you know, because I think some of you have done a titration in your Chem 1 classes, maybe, maybe not. Do you know what the substance is called that changes color when you reach the equivalence point? Do you know the name? It's something called an indicator, okay? And there's tons of indicators out there. The point is, most chemicals that we deal with are clear, most solutions. We need something that changes color to give us a visual cue we're at the equivalence point. Okay? So this word endpoint just means the point where the indicator changes color. Okay? And we will do some titrations this year, and we will definitely use some indicators. And they come in all different colors. So let's get to some of the math here. This problem, oh, and by the way, again, for those of you that printed out the PowerPoints, I made a change here and here. Okay, I think on the previous time, when you first printed it out, it said lithium hydroxide. I've changed it to calcium for a reason. Okay, so the problem says we have 50 milliliters of calcium hydroxide, there's our base, requires, here's that combination we're going to see 1,000 times over, a volume and a molarity. And tell me, guys, tell me one more time, what can you immediately solve for? Moles, okay? So I can immediately get moles of nitric acid. We are asked to find this. What do brackets mean? Molarity. And molarity, just refresh my memory, is what divided by what? Moles over volume, and to be specific, what unit of volume? Very good. Okay. What do you think is the very first thing you should do before you calculate anything? Even before that, what do you need? A balanced equation. Okay. Do that, please. Okay, let me make sure you guys understand something. It says this is required for that, for neutralization. And what are they trying to tell us here with this word? Where are we? We're at the equivalence point. Be careful, okay? The previous slide, I made a point to change this on the PowerPoint. It didn't say moles of acid equal moles of base. It said moles of H plus equal moles of OH minus, okay? If I write out my balanced equation, all right, I want you to notice something. And by the way, water is your other product here. I'm going to write it in a way that's maybe a little different. Maybe you've never seen this. I don't write water as H2O. I write it this way. It's the same thing. The reason I write it that way is because in my mind it makes the balancing easier. Don't think of water as H2O. Think of it as hydrogen hydroxide. Okay? Think of them as like two separate things. So when I go to balance, one hydrogen, one hydrogen. Okay, that's balanced. One nitrate, two nitrates. Okay, so I gotta fix that. One calcium, fine. Two hydroxides, one hydroxide, so I gotta fix that. Now it's balanced. Okay. I just find it easier to balance if you think of water as HOH, but that's totally personal preference. Okay. So let me come back to what I was saying. I didn't say on the previous slide moles of acid equal moles of base. I said moles of H plus equal moles of OH minus. If you wish, you could take this down to your net ionic. That's fine. But let me show you another way here. All right? This times that. Let's get a number. Be careful with your units. Okay, now, if my acid and base were in just a 1-to-1 ratio, then I could right away say, okay, this many moles of acid, that's also going to be the same moles of my base. The reason I changed lithium hydroxide to this one specifically is because they're not in a 1-to-1 ratio. But don't panic. All we've got to do is do a one-step conversion, moles of HNO3 to moles of calcium hydroxide. Do a little stoichiometry, no big deal. What do brackets mean again? Molarity, which is what over what? Not grams. Moles over liters. Okay, well I've got my moles. Fine. Now be careful. What volume do I want here? Liters, yeah. So what volume do we want here? Yes, this is in milliliters. We need to change it. And let's do that. Final answer right here. Let's try another one. I'm going to set it up and you're going to finish it. Let's look at what we're given. Here's that combination again and again. What can you immediately solve for?
Moles.
Moles. Okay, you're going to get so sick of me asking you that. Moles of hydrochloric acid. We're going to mix it with, there's this combination again, this base. And it says, what is the concentration? What's another word for this? Molarity of the excess H plus or OH minus. Let's just refresh our memories here. What is the situation when you are given amounts of both of your reactants? It's a limiting reactant problem. Okay? So, here's what I want you to do. What's the first thing you should do before you even look at your calculator? Come up with a balanced equation. And then, because I know that you all now know how to do a limiting reactant problem, here's what I want you to do. Use your balanced equation, use the information given to us to figure out which reactant is the excess reactant. In this case, I actually am not asking what the limiting reactant is. I'm asking for the excess. Don't worry about the fact that these are ions. We'll deal with that later. Balanced equation, figure out which one is your excess reactant. Okay, let me just talk out what I've got up here. All right, the very first thing I did was I used my volumes, my molarities for each reactant, and I got moles of each one of my reactants. Okay? And let me tell you something, okay? To carry out a limiting reactant problem, okay? And at this point, I'm expecting you to know how to do that. You take the moles of each of your reactants and convert to one of your products. It doesn't matter which product you pick. Some of you may have picked water, and that's okay. As long as you convert them to the same product, it's fine. Let me say one other thing. You don't have to convert all the way to grams of that product. I mean, you can if you want to, but you don't have to. You can just get into moles if you like and stop there. The only reason we've typically so far this year been going all the way to grams is because a lot of times our limiting reactant problems asked for how many grams of product can be made, but I'm not asking that in this case. So, the reason I have barium hydroxide circled is because it was the reactant that gave me the larger of the two values. Okay, that's a little different than what we've usually been doing. Okay. Now, I know how much barium hydroxide I had at the beginning of this reaction. They are asking us to figure out how much hydroxide, but let's use just barium hydroxide at this point, how much is left over. Can you look at what we've got here? Tell me what's a way I could calculate how much barium hydroxide was consumed. There's two ways to do it. She says convert moles of HCl into moles of barium hydroxide. Why do you want to start, and it's correct by the way, why do you want to start using HCl? You got it. I know that all of these moles are going to be used up, so let's use this number to see how many moles of barium hydroxide will be used up. Let's just make sure we understand what just happened. Barium hydroxide is our excess reactant. There will be some of it left over in the end. This is how much I started the reaction with. This is how much was consumed. So what do I do to find out how many moles remain, are left? Subtract, yeah. Starting versus consumed. almost there. Let me refresh your memory that this particular problem didn't say what is the molarity, what is the concentration of the excess barium hydroxide. It said, what is the molarity of the excess H plus or OH minus? In this case, I know it's going to be OH minus. The point is, I'm not in moles of OH minus at this point. I am in moles of the whole compound. And we did a little of this in chapter 3. Some of you will have done it in Chem 1, some of you will not. But I need to get into the right units. For every 1 mole of barium hydroxide, how many moles of hydroxide are in there? 2. What do brackets mean again? Okay. Well, I've got the moles. And this is what I was thinking on that previous problem where I got a little mixed up. The reaction is over. We are at the end. I had 2 solutions. I have poured them together into one big beaker. What volume should I use here? I've poured them both together. Do I want the individual volume of barium hydroxide? What do I want here? Both of them. I want total volume. 75 milliliters plus 225, that's 300 milliliters or 0.3 liters. Just to make sure we've got this, guys, what would the molarity of H plus be at the end of this problem? Some number? 0. There isn't any H plus. Remember, that was my limiting reactant. Limiting reactant means it's gone. So let's just recap what we have done so far. Okay? We have done precipitation reactions. We've done precipitation reactions. We have now done acid-base neutralization. The last part of chapter 4 has to do with oxidation reduction reactions. And usually I will shorten that and call it a redox reaction. That's just, a shortening, reduction, oxidation. Now, tell me please, this term oxidation states, that's just a fancy term that really means what? Charge. Yeah, it's just a fancy term that means charges. Okay, and a redox reaction is defined as when you have 2 or more elements changing charge from reactants to products. Okay, we're going to look at an example in just a second. I have a little memory trick for remembering what does oxidation mean, what does reduction mean. All right, and here it is. It's a little silly. What animal do you think of when you see the word Leo? Lion, okay? Leo the lion says grr. They don't say roar, they say grr. It's a fact, look it up. Okay? But there it is. Okay? If you have a loss of electrons of some element from left to right, reactants to products, it has been oxidized. If an element gains electrons from left to right, it has been reduced. Some of your Chem 1 teachers use a mnemonic device, it's like oil rig or something. Yeah, I mean, that's fine, whatever works for you. This is mine, but here's how you identify what has been oxidized, what is reduced. We're going to go element by element, and assign charges. So you guys tell me, within this compound, what is the charge of iron here? Plus 3, okay. Oxygen is always, okay. How about an element by itself? 0. Here's another one by itself. Aluminum is plus 3, and here's oxygen again. Okay. Well, in English, we read left to right. So we're going to look at these reactions from left to right. Look at what's happening to iron. It's going from plus 3 to 0. Remember, guys, electrons are negatively charged. What's happening to iron? It's gaining electrons, so iron is the element that is being reduced. What's happening to oxygen? It stays the same, nothing. Okay? And aluminum, which goes from 0 to plus 3, it's lost electrons, so it must be the thing that is being oxidized. Okay? Now, guys, in a redox reaction, you have to have one of each. You've got to have some element being reduced and some element being oxidized. Okay? They're not called reed-reed reactions or ox-ox. Reed, ox. Okay? Now, again, as the whole point is that you can assign charges, so we need to look at these rules for assigning a charge to an element, and most of these are very common sense. Okay? So, first of all, you guys just told me what this is really saying. An element by itself has an oxidation state of 0. Fine. Well, what if it's not just a neutral element? Okay, so for example, if I had, I'm just making this up, aluminum plus iron with a plus 2 charge yields something, something, something. Okay, who cares? The point is, what's aluminum's charge here? 0. What's iron's charge? Plus 2. Okay. It just means if an ion is in your equation, its charge is what its charge is. I don't know how else to say that. Okay. That's what number 2 means. If you're given a charge, use it. Okay. Oxygen is going to be -2 most of the time, unless you see a compound that has the word peroxide in it. Peroxides are -1. That's not going to come up very often. When you see hydrogen in a covalent compound, it's always going to have a charge of +1. That's not, a big mystery. Hydrogen is in group 1. It should have a charge of +1. Okay? This statement, again, you already showed me that you know it. If you are trying to figure out the charge of some element, you figure it out by realizing that compounds are going to be neutral. Let me explain what I mean by this. Let's say you were not given a neutral compound, you were given a compound that has an overall charge. And you're supposed to figure out the oxidation states of these elements. Well, what is oxygen again? Its charge is always what? -2 times 4 is -8, right? We are trying to figure out what's the charge of sulfur there. It's not supposed to add up to 0. It's supposed to add up to -2. So -8 plus what equals -2? +6. Okay? That's what this statement means. That's all. Okay? So, this is where we're going to end today, and this is so simple. all I want you to do is above each element, write its oxidation state, its charge. I'm sort of holding off on this one for a reason. I'm seeing some confused looks, and you should have a confused look on your face. What's the charge of oxygen again? -2 times 4 is -8. What? Go ahead and say it. What would this be? 8 over 3. Positive 8/3. Okay, that's weird. Okay, guys, this compound does exist. I didn't just make that up. It's a bit of a strange compound, and this is kind of just extra information. Fe3O4 is sort of, it's like a complex that involves iron compounds with both oxidation states. Iron can have a +2 or a +3 charge. This is almost like a hybrid of the two. There's some FeO and some Fe2O3, and they are complexed together. Okay? And so if you think about this, all right, 8/3, divide that out. What do you get? Not an average, but like a hybrid between +2 and +3. Okay? You don't need to know that. The reason I did this is to make sure that you are actually doing this process correctly of figuring out what the unknown element is, what its charge is.